Hello everyone! In this video, we're going to be looking at something that might be a slightly better approximation for area than RAM, the rectangle approximation method. Now I know what you're thinking, okay Mr. Doolin, we have integrals. Why do we need to keep approximating the area? Well, again, not every integral can actually be evaluated analytically and can take some intense computing power to do. So having a couple decent approximation methods is still valuable. Today, we're going to look at using trapezoids to approximate area instead of rectangles. So imagine, whoop, that's weird. There we are, we're back. So imagine we have some function real quick. Whoops, it went away. Here it is, it's back. Something curving up like that, I don't know. And you know, the problem with the rectangles is you had a lot of overestimate or a lot of underestimate. Well, couldn't we do a little bit better job of approximating the area if instead of a rectangle, what if we used a trapezoid? Because a trapezoid is really just kind of like a rectangle plus a triangle, right? So if we, have our point here and then our point here, and we can connect them. So on my current shape, this would actually do a pretty decent job. It's not going to be perfect, but this would actually do a decent job of getting my area, right? And you'd have a little bit of overlap, a little bit under, just depending on how the function curves around. But it's really not too bad to calculate, because if nothing else, if you forget how to do a trapezoid, you can always do the rectangle and then the triangle above it. Let's see. Your geometry teacher would have told you the area of a trapezoid is the average of two bases times height. But for us, the trapezoid is kind of on its side, because if you look at any individual trapezoid that I've drawn on this diagram, it's really shaped like this. And so I think it's going to be helpful to change up the definition just a little bit here. So what you called bases in geometry are now heights or function values, and what you called the height in geometry is really now a width. So how about let's redo this here. Why is my eraser not working? Yikes. Okay. So let's change it up. Let's say for us, to help us remember for the AP test, the area of a trapezoid is the average of two function heights. So I'm using a and b as different x values. Again, divided by 2 because it's an average, times the width. Or in place of width, you could say, b minus a as well. So I've got a little commentary over here, basically about how trapezoids are better than rectangles. Okay, let's use it. So use the trapezoid rule with n equals 4, so this would mean 4 trapezoids, to approximate the value of the integral from 0 to 4 of x squared. So hey, how about first thing, just to get something to compare our answer to, let's get the real answer here. From 0 to 4, x squared dx. Our antiderivative would be x cubed over 3, because we're using the power rule in reverse. I would evaluate this at 4 and 0. So 4 cubed divided by 3 minus 0 cubed divided by 3. Well, hey, that one's 0. So let's see. 4 cubed is 64, and then over 3. So let's see. That would be 21 1/3. Right? Because 60 would be 20, 63 would be 21. Yes. Okay. And it goes on. So that'll be our thing that we compare our answer back to, just to see how well we did. Okay, well, if we're going to make 4 trapezoids, that means we need the function's height at 5 different places. Basically, if I was kind of just to make a number line here or something, we're going to need the height at 0, 1, 2, 3, and 4. Whoops, okay. So filling this in, this does make 1, 2, 3, 4 trapezoids, but notice how I have 5 heights that we really need here. So let's just, I don't know, let's make a little t-chart. How about? So I got my x values, And then I got my f of x values. And one thing that separates trapezoids from RAM is that in trapezoids, you're definitely going to use both endpoints. Remember how with RAM, you either discounted the leftmost endpoint or the rightmost endpoint? I mean, unless you did midpoints, then, but that was different entirely. With trapezoids, you want them both. So let's go ahead and get the y values for every integer from 0 to 4. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 9, 16. Okay, so then, if we are going to use 4 trapezoids to approximate this area, I'm just going to repeat the formula I have over here in green multiple times. So like my first trapezoid is going to use the leftmost height, excuse me, plus the one to its right. We're going to average those two and multiply by the width between the x values, so that'd be times 1, and repeat forever and ever. Instead of using the function notation, I'm going to go ahead and plug in the y values. I hope that's okay with you. So really this would be 0 plus 1 over 2 times 1. I'm going to go ahead and include the times 1 just to keep you used to it for now. And we'll just repeat going down the line. So my next trapezoid would use heights 1 and 4. So 1 plus 4, average them, and then times my width is 1. My next trapezoid is going to use 4 and 9. Its width is 1. And let's see, my last trapezoid is going to use 9 and 16. Again, its width is 1. So let's see. This is something we can punch in a calculator. It'll take a little while, but it's something we can punch in a calculator. And this would be about 22 units of area. So if our actual answer is 21 1/3, not too bad, right? And we only had to use 4 trapezoids. Okay, for my next parlor trick, we're going to repeat our estimate. This time we're going to use 8 trapezoids instead of 4. So we're going to see how does it get better as we add more, just like we did with rectangles. I know we expect it to get better, but let's see how much it gets better. Now, I already have a handful of the y values up here, but if we're going to use 8 trapezoids, now that means my width is going to be a half. So I need to go back and I need to get some more y values at all the 1/2s as well. So I'm going to make just another T-chart because I ran out of room there. So I need like 0.5, 1.5, all the 0.5s. There we go. And then we'd still go back to 4. So let's see. 1/2 squared is 1/4. Let's see. 1 1/2 squared is, nope, it's 2.25. Whoops, I goofed. 2.25. 2 1/2 squared is 6 1/4. And then 3 1/2 squared is 12 1/4. So now I'm just going to repeat my calculation, but like for my first one, it's going to be 0, the height at 0 plus the height at 1/2. I'll average them, and then I'll multiply by the width, which is now 1/2 or 0.5. So that's what's going to change our calculation a little bit. And I'm just going to repeat this for every single trapezoid. So our first one, again, would have the first height would be 0, and then the second height would be 0.25. We're averaging that, and then our width is 1/2 or 0.5. My second trapezoid would reuse the height of 0.25, and then it would also use 1. Again, average those, multiply by the width. Okay, I'm not going to narrate doing this for every single one, but just enough to get you the idea of where we're going. So now I'm reusing the 1, use 2.25, average them, multiply by the width, and we'll go forever. So I won't make you sit through that, but I am going to get it all on the screen in case you want it. Boom. There you go. That's every single trapezoid there. And if you punch all of these calculations into your calculator, you will find our approximation gets so much better. Well, it's a little better, right? Our actual answer is 21 1/3. We got a whole 0.5 better. Not very much percentage-wise either. So honestly, trapezoids do a pretty good job, even if you're not using very many of them. Let's talk about how do we determine if trapezoids are going to give an overestimate or an underestimate. And so it's really hard to see when I'm sketching it out. I could have probably done a little better job with my example up here. But it specifically depends on concavity. So if you have a function that is concave up, you're going to see, hopefully, maybe I'll zoom in here, that your trapezoids are going to ever so slightly overestimate the area. So concave up, overestimate. And then similar conclusion for concave down. Whoops. Zoop. You're going to find that your trapezoids, especially if you blow it up, so let's do here and there, you're going to find that your trapezoids ever so slightly underestimate. And it's more obvious the more quickly the slope is changing there. So you're just going to see a slight underestimate. Okay, on the next page, I just wanted to show you a shortcut here. So let's see, turning the page, boom. So in our calculations, did you notice how we were rewriting divided by 2 and times the width a bunch of times? That was kind of redundant, right? You can simplify your work just a little bit. And this is just a shortcut, so you don't necessarily have to remember it. It is formally actually called the trapezoid rule. Trapezoid rule. And it's at the area. Now this only works, well, I'll come back to the rule in a second here. So the area approximation using trapezoids can be found by factoring out 2 things. You're going to factor out the width, which we used every time, right? So we always were multiplying by 1, or we were always multiplying by half in the previous problem. And you were always cutting the 2 y values in half. So again, if you flip back here, see, look, like in the second problem, our width was 1/2. Look at how often we had to write it. You know, I'm lazy. I don't want to do that. And then we had to cut every set of y values and divide by 2. Like, I don't want to do that. So I'm factoring both of those out. Then, the only other thing I want you to notice is how often we reuse certain y values. So the first y value and the last y value only show up once. But every other y value shows up twice. All the interior ones show up twice. Well, I'm going to run out of colors here pretty quick. Ooh, can I change it? Will it? Oh, it permanently changes the color. I don't like that. Oh, well. You get the point. I want this back as red. So see how these all show up twice, and you can keep following it through. Every y value shows up twice except for the 2 endpoints. So in our rule, you can say it's a height 1 or function output 1, whatever you want, plus double the second one because you use it twice, double the third, ... however many heights you got, plus 1 single height n, the nth height. That would be like the last one. So h1 and hn are your 2 endpoints. Here's the deal, though. This only works if your width is uniform. Because otherwise, you can't factor out the w if it's not the same number every time. So in these functions where, like I told you, in the problems where I told you, hey, make 8 trapezoids, make 4 trapezoids, make 16, I don't care. You would divide them all equally because you're a sane human being. I like to think. I don't know. Some of you are close to proving me wrong. We'll see. But as I've told you many times at this point, AP, College Board love to give you tables of values, like you'll see on the next page here. table of values. And unfortunately, we won't be able to use our shortcut there because all the widths are not constant. But I just wanted to make you aware, here's a little time saver. So what would it look like if we were reworking the problem from the front page? So I actually just have the exact same problem, n equals 4, same function. Now you'll have to kind of flip back and forth if you want the y value, or I've actually got them here. I don't have to flip back and forth because I've got it on my separate notebook. So with n equals 4, our width was 1. So our area then would be 1 divided by, well, 2, because we have to divide everything by 2, right? The first height from the previous page was 0. The second height was 1. The third height, whoops, that's plus, was 4 times the third. The next height was 9, and then our very last height was 16. So again, I'm not doubling the 0, I'm not doubling the 16. Everything in the middle gets doubled. Punch this out in your calculator, still get 22. A little bit faster, a little bit cleaner. Remember, the AP exam, unfortunately, is a race against time, which is complete bullcrap in my opinion. But alas, that's the game we're up against. So sometimes you got to play the rules of the game, even if you don't like it. Same thing with n equals 8. I just want to show you how we can make that quicker. Again, this time our width is a half. So you'd have a half, or 0.5 or a 1/2, and then you're going to divide it by 2. And then again, just use all those y values. So the first one was 0. Double all the interior ones. Let me see, where are my interior ones? Here we go. 0.25 plus double, yeah, you could even, if you wanted to get even crazier, you could do some factoring with the ones you had to double. I don't know if that's worth worrying about, but you certainly could. 2 times 1 plus 2 times 2. You get the point, right? I mean, we're still going to end up putting 9 numbers in here, but at least we wouldn't have to write that many. Again, this problem, because it was 8, still takes a while, but hey, this looks a little better than we had on the front page, right? Okay, for my last problem, we're going to look at an AP style problem. So let's turn the page. Okay, so here we go. We have a swimming pool. It is snowing outside as I record this video. Gone are the days of the swimming pool in summer, alas. All right, swimming pool, 25 feet wide, 40 feet long. We are given a table showing the depth at various positions from one end to the other. Okay, so here's what I want you to envision in your mind's eye. The top-down view would look like this. So we'd have 25 feet wide by 40 feet long. But if we were to take a cross section, like if we were to slice right here and then kind of flip it out so we get a look-see at what's going on, really we'd see something like this. So this would be like the front of the pool. There's your surface of the water. Here's the height getting deeper and deeper as you get farther and farther to the back of the pool. So this would be like the back, which still lines up over here. We'd still have this length of 40 feet across the length of the pool. The width would still be 25, but now we have this table which helps us out with the depth. Our job is to, whoops, I guess I kind of put these out of order here. We're supposed to come up with an expression for the volume of the pool and calculate, at least as best we can. Let's use some trapezoids to get there. So let's take a look here. We are given all a set of points. We are not given a function. So basically, we're going to use as many trapezoids as we can. So looks like we're going to use 8. And then for the volume, though, you might be thinking, well, wait, hang on. Mr. Julian, you said this gets area. How are we going to do volume? Well, what is volume? But this area over here times what would kind of be the width or well, depth is a bad thing here. Let's remember the area is including depth and length. So the only other thing we need here is width, which is at 25 feet. So if we can approximate this depth times length area, I know it's kind of weird. It's the area of the cross section, but that'll work. If we can approximate this using some trapezoids, well, we can come up with a decent approximation then for the volume of the pool. So let's see. Our area using our trapezoids, yeah, let's just call it A trap. That'll work. Now, again, like I told you before, you can use the shortcut if you have consistent widths. Well, 0 to 5 is 5. 5 to 7 is 2. Okay, we're kind of in trouble here, right? We don't have consistent widths. So unfortunately, we're not going to be able to use the shortcut rule. That's okay. We're still good at doing calculations anyway. And full disclosure, yeah, okay. I've never seen an AP problem give 8 depth, make you make 8 or 9 trapezoids, or I guess 8 trapezoids. The most I've ever seen is like 5. Honestly, I should just go into this problem next year and delete like the last 3 rows, but I haven't. I'm sorry. The logic is the same. So let's just take a second to look through it here. Okay, so remember, area of a trapezoid is always width, and you can actually do the width at the end if you want. So how about average of the two heights? In this case, that would be depth. Divide by 2 because you're averaging times the width. So like my first 2 here, my width between them was 5. That's why I scratched all those off to the side. And we'll just keep on going. Reuse the 5.1. Got 6.8. Average them. What's our new width? Our new width was 7. I'm going to keep going. You catch up if you want. Whew, that's a lot of writing. I really do need to delete like the last 3 there or something, make this a more reasonable problem. So there's our trapezoidal area. And then to get the volume, remember we just said, well, the volume is going to be this sideways area times 25. So I'm just going to take my answer times 25, push the buttons in the calculator, a little more than 7,000. Remember, if you're given context, answer in context. I see our measurements were given in feet. So I'm going to leave myself a note that the area, or sorry, the volume is feet cubed. All right, good stuff today, guys. Hey, that is the end of Unit 4. That is the end of our unit on approximating areas and beginning to calculate them exactly. See you tomorrow.